Hi, I'm Justin Ansell,
I'm Ida Clara.
I'm Eric Oliveira.
and this is our EE475 final project. It's a proof of concept smart home device that tries to mimic the functionality of a fully voice controlled smart home system. It can recognize spoken keywords and control smart home devices based on what is said. The actual smart home system would be connected to a full house, but for the scope of this project, we chose to limit it to just a self-contained device instead.
But just inside this is this proof of concept. All we really wanted to show is that we can train an accurate and robust model, flash it onto an embedded system, and make sure we have a full real-time end-to-end system that works and can be verified through peripherals.
We have a couple peripherals as outputs for our keywords. We have the RGB LED and we have the LCD screen. And the keywords are white, red, green, blue, and off for the RGB LED. And we have time and temperature for our LCD screen. We also have error handling for noise and unknown words. So that helps us with the accuracy. And we have the button here, so when pressed, it activates a 4-second window. And that's when you speak into the microphone, and that's when you enter the keyword as well. White. Blue. Red. Green. Off. Time. Temperature.
Noise test. No command detected. Let's try an unknown word, something it wasn't trained on. But it should still identify human, which is different than no command detected, which stands for noise. Blah, blah, blah. It says, sorry, I didn't get that.
One of the most challenging parts of our project was gathering good data. Our data consists of 30 to 60 second long audio files of speakers saying a voice command multiple times. The speakers are ourselves and our friends and families. We established a naming convention of label, speaker, number of that speaker uttering that label, and full to indicate that it is a full recording with repeated utterances. Adhering to this naming convention is crucial because we extract the vectorized label of the data point based on its name. For our unknown class, we recorded some of our speakers saying hundreds of random words. We also used Qualcomm's keyword speech dataset, which contains multiple speakers saying a few wake sentences. To train our model on generic background noise, we use a Kaggle dataset of random 3-second chunks of noise from all sorts of environments. To split individual utterances from the raw recordings, we wrote a file chopping function, which parses a WAV file and extracts all detected windows based on user input. We had to iterate this process through all of the raw recordings with tunable parameters like threshold and window length to adapt to the different recording settings of each of the raw recordings. We also artificially expanded our training dataset through some basic audio transformations to increase model robustness. The model's input is actually an MFCC matrix of curated audio chops. MFCC stands for Mel Frequency Cepstral Coefficients, and this is a common audio feature. The model's input are the MFCC matrices. We then run that through a convolutional layer, 2D convolutional layer with 64 kernels, which are 4x4. We do some batch normalization, some max pooling. We use dropout to avoid overfitting, which basically masks some of the kernels to 0 so that the other kernels need to learn on their own. We then repeat the process, another 2D convolution, this time with 3x3 kernels of 64 size. The final convolutional layer has 128 kernels, which represent more abstract features. We then take a global average of these 128 maps and set that as our first dense layer, which connects to the final dense layer that has 9 neurons. These correspond to our 9 classes and are the predictions of the model. We trained our convolutional neural network with an atom optimizer and a cross-entropy cost function. The model actually achieved 100% accuracy on test data.
The system gets the current time directly from Python's datetime module, retrieves the temperature by making an asynchronous request to the Python weather API, and lights the LEDs by adjusting the PWM duty cycles on the red, green, and blue GPIO pins.
We put all of the components inside a custom 3D printed housing with a back that slides off for easy access to the internals. Our system is powered by a Raspberry Pi Zero 2W, which runs a full Linux operating system and connects to all the other peripheral devices.